Good morning, ladies and gentlemen. Welcome to the video lesson for Chapter 5, Section 1, the third set of notes, which covers piecewise functions. This section starts off by reviewing sort of what a function is. When we write a relation or a function, we're always given a rule. For example, here we have f of x equals 3x squared minus 4. So that rule is for any x value. If we want to know the value of f of 2, we would simply follow that rule, meaning we would take that 2 and we would plug it in for x to get f of x, or y, out of the equation. So we'd be looking at f of 2 equals 12 minus 4, or 8. However, it's not always that simple. Sometimes the function will have more than one rule depending on the domain values. As such, you'll have to recognize which rule you're supposed to use based on the domain value that you're being asked to evaluate. These functions are known as piecewise functions. Okay, for instance, if we had a function f of x where our rule was 3x plus 2 if x is less than 1, and 5x minus 1 if x is greater than or equal to 1. Again, you'll list your rule, and it will also list the domain for that rule. So anytime that your x value is less than 1, you'd be using the first piece, the first rule. Anytime where it's greater than or equal to 1, you'd be using the second one. So here is a graph of a piecewise function. You'll notice that there are two different pieces to this piecewise function, and there should be dots on the ends of those. Okay, as such, there are two different pieces written. Now, when we're on a graph and we're being asked to evaluate, that's still the same process that has always been on a graph. If we want to know f of negative 5, okay, that's an x value. So we're being asked when x is negative 5, right here, what is the function value? Well, according to this point, negative 5, 5, f of negative 5 is equal to 5. Same thing for f of 4. We'd go over to x equals 4 and find that point on the graph. That is the point 4, 5, which means that when x equals 4, f of x equals 5. And f of 2, well, that one's a little bit tricky. We have to find the closed circle at f of 2. Okay, we want the closed circle because that is the value that is actually in the domain, whereas it is not the point 2, 1 because that is an open value. So f of 2 would be 4. So on example 2, we're given an actual function, not a graph, and we're asked to evaluate that function. So again, this is going to come down to, are we looking at piece 1 or piece 2? And it's all about the domain. Okay, the domain values tell us what we're looking at. Okay, so, and I'm actually going to do piece 2 in red, that way we can see a difference between the two. Okay, so when we are looking at the value g of 2, x equals 2 is piece 1. Because 2 is less than or equal to 3. Okay, so we're supposed to evaluate g of 2 by plugging that into the first rule. 2 times 2 minus 1 would give us g of 2 is 3. Part B says g is 3. Well, when x equals 3, that's still piece 1. Because 3 is less than or equal to 3. So we're still plugging into piece 1, which means that g of 3 is 2 times 3 minus 1, or g of 3 is 5. Okay, then we get to the next one. Well, g of 7 is saying x is 7. Well, that would be piece 2. Because 7 is greater than 5. So we're going to say g of 7, and we're going to plug into the second rule, 7 squared plus 3, meaning that g of 7 is 49 plus 3, or 52. Now on letter D, we're looking at x equals 4. X equals 4 is not in the domain of either piece, which means no solution. 4 is not less than or equal to 3, and 4 is not greater than 5. So it doesn't fit either piece's domain, meaning it is a no solution. Finally, g of 0, well, x equals 0 would be piece 1, because 0 is less than or equal to 3. So we would say g of 0 is 2 times 0 minus 1, or g of 0 is negative 1. That's how we evaluate a piecewise function. We have to consider the x value they're asking about, which domain does that fit into for which rule, and then plug into the appropriate rule. Okay, now, so next up is step function. A step function is a type of piecewise function where every number in the domain is paired with a single integer value. As a result, the graph ends up looking like a staircase, hence why it's called a step function. So one example of a step function is called the greatest integer function. And the greatest integer function, we are referring to f of x equals double bracket x. Okay, what does that do? Well, the double brackets mean round down, always down, to the nearest integer. Now remember, your integers, that's the number set that includes all of your negative and positive numbers, without decimals, without fractions. So on example 3, we're just rounding. Again, if it's double bracket 3.7, that would round down to equal 3. 2.1 would round down to equal 2. If it's already an integer, it doesn't affect it. So 5 is unaffected. It's sort of like when you're plugging a positive number into the absolute value function. That doesn't do anything. Now where this gets tricky is when you're around 0 and when you're negative. See, negative 3.6, the next integer down is actually negative 4. Negative 1.1, the next integer down, is actually negative 2. So please be careful when you're dealing with negatives. Don't do too much. Now we can also evaluate greatest integer functions relatively easily. If we're asked to find k of 1, we're going to plug 1 into that expression, 4.8 minus 3 times 1. Well, double brackets still get treated like parentheses. We would still need to simplify the inside first. So we would end up with 4.8 minus 3, which is double bracket 1.8, which means that we're going to round that down to 1. Okay, same would go for any of these. And I'll alternate colors so that we can keep our work straight here. K of 2 would be double bracket 4.8 minus 3 times 2. That would be 4.8 minus 6, or negative 1.2, which means it would round down to negative 2. So k of 2 is negative 2. Okay? 0, again, we're still we're evaluating. We've done this 1,000 times. 4.8 minus 3 times 0 would be 1.8 inside our double brackets. And we would round that down to 1. Okay, etc. So we're just going to finish these out here. K of negative 1 would be 4.8 minus 3 times negative 1, which would be double bracket 7.8 because it would really end up being 4.8 plus 3. And then we would round that down to 7. And we can even plug in partial numbers just as easily. 2.5, double brackets, 4.8 minus 3 times 2.5. So we'd evaluate 4.8 minus 7.5, which would be what, negative 2.7? So hoping I don't get that wrong. Which would round down to negative 3. All right, so there's example 4. On to graphing a step function. Okay, if we want to graph y equals greatest integer x, we can do that just like we do any function. Okay, when we plug in, say, 0, that is unaffected because 0 is an integer. Okay, double bracket 0 is still 0. Okay, but if we plug in, say, 0.2, that would also get rounded down to 0. Or 0.7, well, that would also get rounded down to 0. Okay, it isn't until we get to 1 that it moves to the next point, 1. And then 1.2 would get rounded down. 1.5 would get rounded down. 1.9 would get rounded down. And when we hit 2, it jumps again. So what that ends up looking like is we have a closed circle at 0, and then every value from 0 all the way over to 1 gets rounded down to 0, creating this horizontal line with a closed circle at the left end and an open circle at the right end. Now when we get to x equals 1, the value has a jump discontinuity. The graph has a jump discontinuity up to the point 1, 1. And then every value between 1 and 2 gets rounded down to 1, creating another identical step. When we get to 2, it will jump again up to the point 2, 2. And that pattern will continue off the ends of the graph. We'll have these 1 unit wide steps, as it were. This is why it's called a step function, extending with these jump discontinuities in both directions, which means that it continues the negative direction as well. Every number between negative 2 and negative 1 gets rounded down to negative 2. Every number between negative 3 and negative 2 gets rounded down to negative 3. So on and so forth until we have our entire graph. Now, just like any other function, we've been talking about how those are affected by values of a, h, and k, and that is definitely still the case. Even with this greatest integer function, the same thing would happen. Okay, so here's a different piecewise function. This piecewise function in example 5, we're going to graph these as well because we don't really have a lot of experience graphing piecewise functions. Remember that this is really 3 different functions because we have the rule and then we have the domain. Okay, so when we look at piece 1, 4.5, h of x equals 4.5, when x is when x is between negative 1 and 1, including 1, but not including negative 4. So what's happening here is we basically have domain values, which creates these vertical sections of graph where this piece exists. So piece 1 exists between x equals negative 4 and x equals 1. And everywhere between those two values, the graph is at 4.5. So if we drew that, that would be a horizontal line running from negative 4 to positive 1 at y equals 4.5. Now the challenging part is that we have to watch our endpoints. Okay, in this case, our right endpoint is closed, but our left endpoint should be open. Okay, our left endpoint should be an open circle. So when we're looking at our graph here, piece 1 should be a horizontal line. Try to get it a little bit better here. Can't quite get it to stay where I want it. There we go. That's pretty good. Okay, with a closed circle on the left end and an open circle, a closed circle on the right end and an open circle on the left end. Then we look at the second piece. Well, the second piece of that function, which we'll do in black, has a rule of -2 from 1 to 3. So again, that creates a separate section of the graph from 1 to 3 where we're using rule number 2. And that section has a closed circle on both ends because we have these less than or equal to signs on both ends of the thing. So we are at -2, closed, closed, and we've got a horizontal line in between them. Okay, then finally our third piece is from 3 to 6, and it is open on both ends. So in that section, from x equals 3 to x equals 6, we graph piece number 3, which is open circle on both sides and a horizontal line at y equals 1. There is our piecewise function, h of x. Again, the domain pieces are where the domain ranges are how we break up the graph. So, let's do another one. Here is one that's a little bit more difficult. Okay, remember that when we do this, one good approach is to graph all 3 pieces in pencil, okay, on the entire graph. Okay, then erase sections that are not included. Which is where you look at the domain. And then consider open or closed endpoints. Again, we need to look at that domain. Okay, remember that these mean open, these mean closed. So, for instance, if we wanted to graph f of x equals this function here, 2x minus 1 when x is less than 2, and -3x plus 5 when x is greater than or equal to 2, that's really 2 separate lines that we can graph. Remember that to graph a line, we start at the y-intercept. So for piece 1, that would be start at -1 on the y-axis, and then use your slope, which is 2, to find the next point on the graph. Up 2, right 1. Up 2, right 1. Up 2, right 1, etc. We could also go down 2 and left 1. Okay, that's our algebra skills coming into play. So that first piece is the line y equals 2x minus 1. Our second piece is the line y equals -3x plus 5. That would start at +5, down 3, right 1, or up 3 and left 1. So our second piece is that line. Okay, that is piece 2, which is f of x equals -3x plus 5. Now the next part here is the key. That is broken up along the line x equals 2, okay, according to the domain, okay? And the blue line only exists to the left of that green line. So we would erase all of the blue line that is to the right of that line, and then consider that the endpoint should be an open circle at 2, 3. The red line only exists to the right of the dotted line, So we would erase the red line to the left of the line and consider that it should be a closed circle at 2, -1. Notice that this graph with the freshly erased and open closed circles considered is now a function because it passes the vertical line test. So that's what we're doing here is we're graphing both pieces and then we're going in and cleaning it up to make sure that we get just the domain sections that are listed in the problem. One more. Okay, graph the following piecewise function. This one's obviously more challenging, but it's going to draw on our knowledge of 1-5. Okay, first we have a quadratic function. Okay, piece 1 is quadratic, and it has an a value of 1, an h value of -2, and a k value of -1, which means we take the parent function, -2, 4, 1, 1, -1, 1, 0, 0, 1, 1, and 2, 4, and we carry out our transformations on it, okay, just like we have done over time. So x minus 2 and y minus 1 is the transformation that we're doing. So that would be -4, -3, -2, -1, and 0 in the x column, and 3, 0, -1, 0, 3 in the y column. Graph those points. So -4, 3, -3, 0, -2, -1, -1, 0, and 0, 3. So there's your first piece without the domain restrictions. Okay, then we've got the second piece, which is a square root with a equal to 1, h equal to -3, and k equal to 0. Which means we're going to take the parent, which is 0, 0, 1, 1, 4, 2, 9, 3, and we're going to transform it. Again, that's the same rules above. X divided by b plus h would be x minus 3, and then a times y plus k would be just y. That's not going to change. So -3, -2, 1, 6 in the x column, and then the y column stays the same. -3, 0, -2, 1, 1, 2, 6, 3. I lied. That -1 should be +1, 2. My fault. Looking at it going, that's not the right shape. That's because I didn't graph it right. Okay, so there we go. So there's piece 2. Okay. And piece 2, okay, that piece is the square root of x plus 3. Okay, and then we've got piece 3, which is an absolute value parent, where a is equal to -1, h is equal to +1, and k is equal to +1. No b value. So for absolute value, we start with the parent function, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Carry out the same transformation we did on the others. X divided by b plus h would be x plus 1. And then a times y plus k would be -y plus 1. So the x values become -1, 0, 1, 2, and 3. The y values become -1, 0, 1, 0, and -1. Graph those points. -1, -1, 0, 0, 1, 1, 2, 0, 3, -1. And remember that those graphs do continue all the way off. Okay, they continue in those straight line patterns to form that unique V shape. That's piece 3, okay, which is our absolute value. F of x is negative absolute value x minus 1 plus 1. Now, from there, we need to go in and restrict the domain. So the domain breaks occur at positive 1, mistake, positive 1, and positive 3 are where the domain breaks happen. Okay? So for the first piece, it only exists below that green line, to the left of the green line x equals -1. It's not actually on the screen, but it means that there would be a closed circle at the point 1, 8 is where that function would end up. And everything else of that function beyond x equals 1 would get deleted. So we'd have a closed circle there at x equals 1, 8. Then the red section only exists between those two lines, so everything to the left of the green line and everything to the right of the green line is going to get deleted. And those endpoints are both open circles. So we have an open circle and an open circle, and they're going to be approximate. And I'm also going to fill in that blue line there where I had to erase. Okay. And then the third piece, the purple, only exists to the right of both green lines, so I would go in and erase everything to the left and between those green lines, and we would have a closed circle at x equals 3, which is 3, -1. And there's the graph of the piecewise function f of x. Okay? Piece 1 is in blue, piece 2 is in red, and piece 3 is in purple. Okay, so that does it for section 1.5, part C. There will eventually be a video of me showing some additional graphing piecewise examples. Thank you very much for your time and attention.